Hey folks, in this video, I want to talk a little bit about when you need to generalize the inductive hypothesis. So let's go way back and talk about a theorem that we use to prove commutativity of addition, plus n Sm. So I want to look at this. Any theorem we've proved before today has not needed a generalized induction hypothesis, unless you might have accidentally done one and then worked it out just fine, but it's never needed it. So let's look back and see what's going on. So how does this proof work? So the way we probably did it back then was something like this, right? Just our sort of conventional induction. Okay, in the base case, if you just simplify, you get back the same thing, right? The zeros kind of cancel, so we can just say reflexivity. Now in this case, let's see what happens. So again, if we simplify, you'll notice that because we've done induction on the thing in the sort of analyzed position by add, um, it's enough for plus to make progress. So when we simplify, we get out something that just sort of says, okay, well, great, this bit matches exactly this bit, and then we can change it into this bit with a rewrite, and then that'll be the same. So let's do it. Right, there's other ways we could have gone. Like maybe you're now totally on team F equal, and you're just like, let's go. Right? There's an argument that that's a much nicer proof. Whatever. So like, a thing I want to note first is like, it's totally okay to do a generalized one. Right? Like, okay, now we have a generalized induction hypothesis. It doesn't change anything, right? Having that extra quantifier, okay, maybe Coq won't be able to guess things sometimes, but it should be able to in any case where it would have worked without it. So maybe you should always generalize, and honestly, there's nothing wrong with that. I think it's just like, well, you want to use the right size tool for the job, right? And especially in a context where people are grading your proofs, um, uh, using the right size tool lets me know that you understand what's going on. Okay, so let's see. Can we come up with rules for when you need a generalized IH? So here's a general rule. There's two things that you might want. There is more than one variable, right? Like otherwise, what else are you generalizing, right? Like if your theorem only mentions one variable, there's no way you need a general IH because there's no other variables. Okay, cool. Variables other than the IH will have different values in different cases. Okay, so we kind of saw that in double, and like in plus NSM, the variables here, like m never changes, right? The fact that it's s of m in one part and just m in one part, okay, that's fine. But m itself never moves, right? We never have to do case analysis on it or anything. That's like a little too general because this doesn't exactly match. Well, when more than one variable changes during recursion in one of your definitions. Okay, we're getting there. That's pretty specific. So like, let's look. So EQB, make this a little smaller so we can see it. Okay, in EQB, you can see, look, we're matching on N and we have to look at both, and then we match on M and we have to look at both, right? Also in the base case, so the base case is usually easier to deal with, but like, we have to match on M to make a recursive call on something smaller on M also. And so, okay, they're both changing. This is a case, EQB is a case where we're going to generally need these varied or more general inductive hypotheses. Okay, what about add? It's plus. Okay, you'll notice here M is kind of inert, right? Add, the way that I think of it, is a process of copying successors from N onto M. So only N changes, we're not going to need general IHs. Okay, so I think this is like an okay model of when you need to do these things. It does have one problem, which is that it's completely wrong. So like ups and downs, right? So we saw the example I chose, double. Double is a function with only one variable, right? So like it's not because of anything to do with the recursion, like nothing's changing there. Like, but then you look at double injective. We've got it on both now. Great. You look at double injective and you're like, well, what are you talking about here? Okay, but think back to EQB true if and only if, right? This equality we know is just the same as EQB. So we could have actually stated our proof something like this: for all n and m, if EQB double m equals true, then EQB nm equals true. And we saw, okay, right, EQB is definitely something that needs general induction hypotheses. So, like, low key, if you're proving something about equality on Nats, then, like, okay, if there's two different things and you're proving equality there, you're probably going to need a general induction hypothesis, because this real equality, like the equal sign equality, propositional equality, is we just showed it's the same as EQB, our computational equality, the one that we can run, and that one is going to require general IHs. But then, like, wait a minute, that's not a good explanation either, because, like, why didn't we need it for plus NSM? Right? It's like, okay, well, it's true that both change here. It turns out that when we're doing induction on n, enough information from n comes out for EQB to make a recursive call, even though m doesn't change, because in either case, we'll get a successor exposed immediately here, and then when n is non-zero, we'll get a successor out of here, and we'll get one out of here in any case. So it ends up just sort of like, okay, it's true that EQB needs both of these to change, but actually just changing n by doing just induction on n is enough to expose a successor in each of these and make the recursive call. So, like, that's a lot. I think that getting to this point and recognizing, like, it's really all about what gets exposed in recursive calls, and there's a deep connection between your inductive hypothesis and recursive calls, and you just need them to match up. And you need a general one when your recursive call might change one of your variables. That's the story. That's a hard story to keep straight in your head. I think long experience is the thing that really lets you know this is something I need to generalize, this isn't. So there's like another, like, more practical, like more operational way of deciding when you need to do it. When you get to a point where your IH ought to work and it's too specific, just go back and generalize it and you'll be fine. Right? That's all it is. Now, eventually, the dozenth time you'll do that, you'll be like, okay, I'm going to get it right in advance. I'm going to get it before I'm going to recognize that that's going to be important. But for now, if you only recognize it, in the middle of the thing or after the fact, that's just fine too. The converse is, if you find that your instinct was to generalize and then you don't need it, you can always fix it. It's just like refactoring a few tactics. Okay, hopefully this abstract discussion makes some sense, grounded in the stuff we've seen before. In the next video or two, we'll be talking a little bit about how you can control the IH a little more manually and explicitly, which ends up being important in some cases. Talk to you soon.